So let's look at 5 points here on a potential graph of the number of dominoes versus length. Now, these 5 points here are relatively well fit by this straight line. We notice that we don't just draw a straight line from the first point but through the last. What we want to do is come as close as possible on the average to the points on our graph. So again, we come as close as possible on the average to the points on the graph. Make the line as close as possible. And going through the first and last point is no way to do that. If you just go through the first and last point, you ignore the contribution of all the other points. That's no way to get a good graph. Your first and last points are going to have some uncertainties in their measurement. Of course, there's not going to be any uncertainty in the number of dominoes. Everybody can count to 5. But the length measurement is going to be somewhat uncertain. So any of these points could be a little to the right or a little to the left of where they've actually been located. If this is the graph of the actual behavior, if this is at least our model of the average behavior, then this model predicts that at some length where the line intersects the horizontal axis, the number of dominoes is 0. That would correspond to no force. That would be the length, or actually in this case the system was holding up the paper bag, so this would actually correspond to the length at which you had 0 dominoes, but you still got the paper bag. And of course that length would be one of your data points, so you would have a data point on the axis. I haven't included one here, but in actually doing this as the experiment was designed, you certainly would. Now, the question is that really the valid curve? Because we could have a little curvature that might actually fit this a little better, but do we really expect curvature? We can't really say. We don't have enough data points. But if we do have a set of data points, let's say this set, then a straight line fits it pretty well. This curve fits it even a little better. So we might have this kind of behavior, or we might have this kind of behavior. And in fact, it's going to turn out that a lot of dominoes, a lot of rubber bands will give you a graph that sort of looks like this, where it's steeper, and then it gets less steep, and then it gets steeper again. And that corresponds to the rubber band being stiffer, then relaxing a little bit, but then you get out toward its elastic limit and it gets stiffer again. And we'll talk about how that comes about. Now, obviously, if we have a lot more data points, let's say that we have, I'll just draw a bunch more data points. Okay. Now, if we have a bunch of data points like this, then they pretty clearly indicate a curvature. With only 5 data points, the apparent curvature can just be accidental. These 3 points here might really indicate a downward curvature on the pendulum count graph. We might actually have a graph that does this sort of thing. That wouldn't make any sense. That would dive us down to 0 count at even a shorter length than this model does. But if we have 3 points like this, the fact still remains those 3 points could indicate downward curvature. If our data is extremely accurate, we would have to accept that there is a downward curvature. But extremely accurate data for pendulums is not going to give you 3 points that look like that. It's even possible that the curve should look like this, and this data point was just unusually high due to maybe a bad count, maybe a bad measure of the length. Bottom line, the more accurate your data, the more confidence you have in the straight line or curve you might draw. One more thing, let me draw a few data points up here to make this point. Actually, I don't need to do that. One thing that we absolutely would not do, let's say for this curve, and let me just draw the red curve, a really bad one. We don't try to go through every point. We don't wander around like this. That's not really a representation of how the force or how the number of dominoes would change with pendulum length. That's not, or how the force would change. It's not pendulum with the rubber band length. Okay, it doesn't bounce around like that. It's going to be a smooth curve. Might be like this, but it's not going to be all wobbly like this. So we don't try to follow our points. Another thing we don't try to do is we don't do these point-to-point graphs. Okay, point-to-point graph up here. That doesn't reveal the actual behavior of anything. It doesn't represent the actual behavior of anything that has smooth behavior. That's not a smooth graph. Okay, so this is a smooth graph. The yellow graph here is a smooth graph. This yellow graph is smooth.